Wow, it's really great to be back here. I remember my first year when I attended the first web program, and I was really excited by all the speakers and programs, and I hope that you're having as much fun as I did in my first year. Thank you all for coming. Just wanted to know how many of you are students here? That's wonderful. Thank you so much for coming. I'm Faisal Nawab, and I'm currently an assistant professor in the computer science department at the University of California in Santa Cruz. And what I want to share with you today is a question that has been in my mind for almost 15 years now. It's the question of whether we are at the beginning of the next technological revolution. And this question began with me as a teenager, just graduating from high school. I was going to KFUPM, which is the university at the East Coast here in Saudi. And at the time, I was very fascinated with technology. I read a lot of science fiction books, but I also read a lot of technologists that are predicting what is going to happen in the next decade, in the next few decades. And one that stuck in my mind is Ray Kurzweil, that despite his more controversial ideas about what's going to happen 50 years from now, had a very interesting graph that I always think about. It's that graph to your right there. This graph shows the progression and the rapid progress of technology. And it's really amazing to see that only in the span of 50 years, we have accomplished so much that compared to 2,000 years of development and of technology before that, all that becomes very insignificant compared to what we did in the last 50 years or 100 years. And one consequence out of that is, well, what is going to happen in the next 50 years or the next 100 years? Are we still going to notice or observe the same level of rapid advancement in technology? And I started to imagine all the things, the wonderful things that could happen. And a fascination of mine was in smart cities, in these large-scale deployments, when technology is actually going to be part of our lives. So far, technology has been restricted inside these metal boxes that we need to look at, that we need to interface with. But I really started imagining that we're going to live inside this technological revolution that is going to change everything around us, that is going to take insights from every action that is happening around us and turn it into a useful action that is going to make our lives better. Having grown up in Jeddah and then living most of my adult life in California, one of the biggest problems for me is the problem of traffic. And when I started thinking about smart cities, I started shifting about thinking that, well, maybe once we have all this data collection and all these sensors and cameras around the city, making insights and making actions and crowd control, maybe we can solve that problem. And I want you to now think about the most pressing problem that you're facing, and maybe technology is going to be able to solve it, especially in this context of a revolution in industry, a revolution in smart cities. And with all this excitement, that is when I decided that I need to go to KAUST. That is a very good place for me to try to start my research career and hopefully be part of realizing this dream of mine of the technological revolution. And looking around the computer science department, I started working with Professor Bassem Shahada, who had very interesting work that really aligned well with my long-term goal. He did a lot of edge research, IoT research, all these devices that can be around the world in a smart city, in a large smart factory. How can we coordinate and communicate between all of them? And that was a very daunting challenge that we started tackling here in KAUST when I was a master's student. And while I was finishing my master's program, I started applying for PhD programs. And I remember asking Bassem, what do you think is going to be the best tool, the best research tool for me to realize this goal of getting to that technology revolution? And at the time, it was 2009, and it wasn't that obvious then. But the cloud was still a new thing. Actually, the first Amazon Web Services cloud, which is now the dominant or one of the dominant cloud providers, was only 3 years old. So we didn't really know about the cloud as students back then. But he told me that if you want to solve problems in the future, you want to have impact in these problems, go to the cloud. So I applied wildly in the US, and I got offers from around 12 universities. All of them, except one, were offers from networks faculty, because I had this background in networks. And only one group gave me an offer to do work in cloud research. And that group was at UC Santa Barbara. And I took Basim's advice, and I said, well, I'm gonna trust you on this. I trusted you on many things before, and that was the right decision, so let me try this. And I started working at UC Santa Barbara with a group on cloud services, on building systems for the cloud, and it turned out to be an amazing journey. Because all these companies that are affecting our lives, from search, from social networks, from content and streaming, all these different companies, the main issue and problem that they were facing in the previous decade is how can I utilize more compute resources? And the cloud was the answer. And it was a very exciting journey because we've observed and helped in building a lot of what's happening in some of these companies. And finally, when I graduated from my PhD, I was lucky enough to get a tenure track position at UC Santa Cruz. And now, beginning as a PI, I thought that now it is time. I've been training for so many years. I've been doing my advisor's work for so many years. Now it's time to bring my dream back and really do something with it. And that dream that I was interested in is to try to utilize technology and computation for this future of integrating humankind with technology. What was really exciting about UC Santa Cruz is that it was only 30 minutes away from Silicon Valley, where all the action is really happening, where all the big impact is happening in computing. And it was a great opportunity for me to go to a lot of different places over the hill, things like HP Labs, Google, RTI, and all these other companies to your right. And I started conversing with them, telling them about what I wanted to do, asking them what are the things that are concerning you. And it turns out that many of these companies are also excited by these opportunities in the edge and thinking that it's actually one step into the future. So I told them, well, now I'm an expert in the cloud. I did 6 years of PhD work on it. Let me try to collaborate with you and help you. And they surprised me with an answer that the cloud is not the right way to support these emerging applications. If you want to do things at the edge, if you wanted to do things that are going to really impact people's lives, you can't really ask a data center that is very far away from you to do the real-time actions and insights that you need in real time. So there was this gap between what the cloud can provide and these applications of the future of technology. So unfortunately, for a few months, all these things that I imagined, I felt that there is a gap that I might not be able to fill. So I started thinking more about it, taking a step back, and I started thinking, what is it that is missing in the current computing paradigm that is needed for us to really get into the next revolution in technology? And it really boils down to two things. The first one is that we need to process more data faster. Once we get into the smart city, industry revolution, and IoT types of applications, the amount of data that is going to be generated is really high, and we need to be able to process all this data. And the other key ingredient in the future of technology is that we need to process this data in real time. A lot of these emerging applications require actions to happen really fast. If you are in an autonomous or self-driving vehicle, you can't really expect to spend hundreds of milliseconds or even seconds to get insights from the cloud. So everything needs to happen in real time. And unfortunately, centralization in general and the cloud were not the answer to these two key ingredients for applications. So I started reflecting on how technology progressed so far, and maybe with this reflection on the past, we will be able to project what is the future and what is the right next step for us as researchers to start doing. So I went all the way back to the 1960s and 70s, and at the time, mainframes were the first type of computing that was supported, where all the resources are with one place at a mainframe, and everyone is connecting to it through a terminal. 10 years after that, in the 1980s, we started having personal computing. And all these PCs had more capabilities, and people would be able to do more on their personal machines. So it started making sense that you don't need to rely on this centralized mainframe, and rather you can just collaborate with your neighbors, with your colleagues, through networks across these PCs. After that, in the 1990s, we started needing to do more in computation. We started observing these dot-com companies that needed to do search in large amounts of data, companies that needed to keep inventories for a large number of products. So we needed to host more compute and more storage in specialized devices that were called servers that users would be able to connect to. And then in the 2000s, now we started noticing the emergence of other types of applications that required large-scale collaboration between users. Things like peer-to-peer services, Napsters, for those of you who remember that, and also things like content delivery networks. All these things required larger deployments that would work in a collaborative way without having this centralization. And finally, now we're in the era of the cloud, where the type of compute and the type of insights that we need to get from data is so expensive that we need to get all these resources in these large-scale data centers where we have tens of thousands of machines working together to solve our problems. And when we notice this progression of these computing paradigms, we observe that there are two forces that are competing with each other on what is the technology that is dominating in any decade. These two forces are the force of consolidation at one hand, which is trying to put things together so that you can have more throughput, so you can do more with your resources. And the other force is the force of distribution, putting things closer to user so that you can do things in real time. And unfortunately, these two forces go against each other. And as we progress in time, as we see that there is this back and forth between these two paradigms. But the other thing that we also observe is that as we progress in time, each one of these two forces take a different shape. And in particular, it's really the scale of each one of these paradigms or each one of these phases. So if you observe what happened in network machines in the 1980s and compare that with what happened in peer-to-peer networking, the scale is very different. So noticing this pattern in computing, I started asking, are we at a turning point? Are we now at the tip of the cloud phase and moving into the next phase of computing, going back to distribution? And thinking about this problem from this context started making sense, because a lot of the things that I heard from companies and collaborators in Silicon Valley is that there is these challenges in the cloud that cannot be overcome for fundamental reasons. And we observe things like the complexity of IoT projects, where some reports say that 75% of these IoT projects fail, and mainly because of the complexity of these projects. And also the data volumes that we deal with are very huge that cannot really be effectively transferred to the cloud. And finally, there are some fundamental issues too, such as the speed of light. No matter how good your interconnects and your communication is going to be, you're always limited by the speed of light from your device to the data center. And what we've noticed is that for all these different companies around the world that are doing edge databases, they are mostly following the same pattern of computation, which is I'm going to collect the data at the edge from all these IoT or smart devices. I'm going to push it to a middle tier, and then finally I'm going to push it to the cloud. And at the cloud, then I'm going to do all my analysis and insights. And this is not scalable. For those companies, without mentioning names, because it's really embarrassing, to be honest with you, to get insights using this approach, it might take a few hours until you get insights. This is not real-time insights. And this is a clear problem that needs to be solved. So trying to think, well, if we know that we're going to a next phase, well, how does that new phase look like? And in my perspective, I think it's really about three main things. The first one, edge processing. We actually need to do processing at the edge. It's not only for static data. It's not only for these inexpensive operations that are typical now of edge computing, but rather we need to think of the edge as an extension of the cloud, as an extension of computing where we do everything there. The other aspect is decentralization. We can't really have any hierarchy or structure to these edge devices because it's an unpredictable environment. A lot of things can go in an unexpected way. So we really need to build our protocols in a way that is going to be decentralized. And the third one that I think is the most interesting is that, well, what is limiting us from getting to this world where there are edge compute and infrastructure that is around a city, a university campus, and so on? And it's really that it's really very difficult to expect that there is one entity that is going to build all this infrastructure, right? Unlike the cloud, where we know that there is a company that can build a data center and that's it. Well, how can you expect a company to build an infrastructure that would cover the whole country, for example, right? So this third ingredient is the concept of a contractor, that the devices, the infrastructure is not going to be owned by one single entity, but rather it's going to be a lot of third parties, maybe telecommunication companies, maybe cloud companies, all these different types of companies, each getting a segment of the population, and we try to orchestrate across all of them. And in fact, this has started to happen, where we see that there is a collaboration that was announced last month between Amazon AWS, which is a cloud provider, and Verizon, which is a telecommunication provider, so that Verizon can provide their infrastructure, their telecommunication infrastructure for cloud access, so that we can build applications that can serve people at the edge. So trying to kind of like to summarize how this next phase look like is about having this large-scale deployment around the world and us trying to take these three components and applying them to a system design that is going to solve that problem: edge processing, decentralization, and the concept of contractors. But at the time, we thought that, well, we're in our academic university. Maybe we are sucked in a bubble, and we think that these are the right solutions, but maybe they're not. So we thought, let's do something different. Rather than just thinking inside the lab, let's try to actually build a research prototype and try to see if people are going to use it. So we started working on a prototype that we called Anilog, which is a data infrastructure that is going to be decentralized, that targets these IoT and smart city applications. And we're going to take these three design components, and then we try to reflect them on this prototype. And we were lucky enough to gather a very wonderful team of people from both industry and academia, a lot of them who had been very successful in taking research prototypes that were built inside labs, and then were successful in actually being deployed in real scenarios. And what really motivated us to build that prototype is that although the idea of edge processing and doing things at a large scale was something that was really professed about 20 years ago, or even more than 20 years ago, it's actually only now is the right time for it to be realized. And that is because the recent research that happened in the past 2 years in decentralized computing and other trusted computation areas now enable us to build a large-scale prototype that is going to be both efficient, highly performant, but also trusted, which is one key issue about these edge and IoT deployments. And in a nutshell, our idea of the architecture of analog is that we try to make a distinction between the different tiers of computation. So at one level, at the bottom, we have sensors and IoT devices that could be around the city or around the campus, and a group of these sensors would contract with one of the contractors. For example, they could contract with a company like STC or like Amazon AWS to host their data. And typically, that's going to be a company that is close to them. So now the data for this group of sensors or IoT devices is going to be close to in the data center that is closest to them. And then after that, there's going to be coordinators that are going to enable users to find what are the contractors that contain the relevant data to them and do all the types of manipulations to take a query or a request and then formulate it in a way that is understood by these contractors. And finally, we interface with clients that are used by everyone. It can be interface with something like a web interface, an SAP interface, or anything that is used by the user. And finally, the magic ingredient here to connect everything together is having a blockchain layer, a truly decentralized infrastructure that will enable all these different components to agree, to achieve consensus in a trusted way. And what is interesting is that it's not only about coordination and consensus. What is interesting about blockchain is that it also integrates a compensation mechanism, so that when I'm trying to contract with a contractor, within the same distribution and coordination framework, I can exchange payments and compensations. And I can also dispute if someone did something wrong. So all these new advancements in blockchain is really the enabler of a lot of how we connect all these different components together in a decentralized way. So to take a quick example of how this can happen, if we take these sensors that are at the bottom and the contractors that are on top of it, all this data is going to move from the sensors to the contractors, and we get queries from users like, let's list the water meters that are showing a so-and-so increase in usage, and through knowing what are the contractors that hold this data, we can send that query and get the information that we want. And this can happen for all different kinds of queries as long as we know where the relevant storage and contractor devices are. So we took and built that prototype, and luckily we've enjoyed very great collaborations now with these companies that are deploying our POC in their applications. And to give you a sense of how one of these look like, this is one of our deployments in a smart city application. So that is a company that does fiber optics in a city in California. And what you observe here is that there is these sensors that are around the city that are collecting all the data. And then we have this unified interface that is going to only communicate with the contractors that are relevant to any query that we are now issuing through this interface. For example, if you see these plots, these are the plots of the readings from these sensors that are around the city. So to conclude, the next technology revolution, I think that it's looming. I think that it's happening right now. And I think a key ingredient in achieving this technology revolution is through designing a decentralized data infrastructure that is going to get all these three design principles and have them in one solution. And hopefully this is going to enable us to achieve these dreams and goals of the industry revolution and a truly smart city. And before I conclude, I'm going to thank the students and collaborators that are actually doing this wonderful work. I thank the undergrads and graduate students at UC Santa Cruz who've been started building a prototype of many of these solutions. And I thank the PhD students that are tackling a lot of these daunting research challenges in the process. And finally, a very quick plug about an event that we're holding at Santa Cruz. It's a symposium about the foundations and applications of blockchain. It's the third year that we're hosting this event. For 2 years, it was held at the University of Southern California, and it's our first time holding it at UC Santa Cruz. We're very excited by it. We have a collection of very excellent keynote speakers. The deadline for submissions is still next month. So if you're working in a related area, I'd love to see your submission there. And of course, let me know if you need any help in the process. Well, thank you so much. Okay, so now it's time for the game of cube rolling. Okay.
Yes, I'm so glad you're close, so I don't have to throw it.
Yeah, thanks for your nice talk. But for blockchain, the proof of labor or the proof of stake, that will happen in the edge. That one question, and then what do you think about NEOM and the KAUST Smart Campus?
These are very excellent questions. So for the first question about blockchain, so I intentionally didn't say anything specific about blockchain because there are properties of blockchain that are going to be needed for these types of applications. But it really depends on the constraints that you have in your organization for the type of blockchain and the type of proof of stake or proof of work that you need to deploy. But if we are doing something like a proof of work or a proof of stake technology, this is going to happen in a decentralized way. So there is the chance that it's going to be a very expensive process. So what we try to do from our end is that we limit our reliance on the blockchain network only for the metadata and configuration tasks. But all the processing, all the requests happen off-chain. Yeah, but that's a very excellent question. As for NEOM and the other smart cities, so you said that there is also an initiative here in KAUST that I think I started hearing in my visit a couple of days ago. I think this is very wonderful. I think really now is the right time to invest in these advances. And I think in NEOM, in this large scale of a city, and also at the scale of a university campus, I think both there is a lot of great opportunities. If someone here knows more about it, I would love to talk more about that. Yeah. Any other questions?
Thank you, Faisal, very much for your interesting talk. And actually, it is very impressive to see how humankind evolving from centralized to decentralized movements over time. And actually, when we look at today's situation, that's not going to be enabled tens of years ago when they were using centralized solutions because of the advancement of technology today. And actually, what's always concerning also people is about privacy of their information. How do you think moving from centralized to decentralized or the other way around would impact the privacy?
This is a wonderful question, and I'm really happy to hear it because this is one of the most challenging aspects that we're trying to deal with. And I think this gets back to what I mentioned a few slides ago, which is now we are at the right time to tackle this problem. And that is because a lot of the privacy and security challenges, we didn't know how to solve them a few years ago. And now we have the technology and the research to do this efficiently. So for example, for the issue of, let's say, secure computation. Until recently, we didn't know how to enable an untrusted device to do computations in a trusted way in an efficient time. But only in the last few years, we started having hardware, things like trusted execution environments, but also software concepts that is going to enable an untrusted entity to provide a proof of the authenticity of their response. Of course, this applies to all the different challenges in security and privacy, and I'd love to talk more about that after the lecture. Yeah. Great. Okay, so I'm going to stick around, by the way, after the series, if you need to talk or discuss or just say hi. So yeah, hope to catch up with all of you.